Hello everyone, I'm Shweta Ketty, Assistant Professor ECE Department. Today we are doing experiment 2 of ADST lab. The experiment is we are designing an oscillator circuit using BJT and LC tank circuit. Okay, this is the circuit diagram of oscillator. Here, if you see, whatever the half of this one, that means till this portion, this capacitor portion, this is entirely same as the experiment 1. Okay, that is a voltage follower which we have which we have done earlier. Okay, in addition to this voltage amplifier, we are giving a additional circuit, that is LC circuit, which we call it as a tank circuit. This particular tank circuit helps to provide a oscillation. Okay, if your in this tank circuit, we are using one inductor and two capacitor. Whenever we are using one inductor and two capacitor, we call that tank circuit as Colpitts Oscillator. If we are using two inductors and one capacitor, then we call it as Hartley Oscillator. For our syllabus, we don't have Hartley Oscillator, we are having only Colpitts Oscillator. So, we are using one inductor and two capacitor. This is the design of the experiment. Now, what do you mean by oscillator? Oscillator is basically, it has to continuously generate the oscillation. It is a self-driven circuit. That means without giving input, it has to produce a continuous oscillation. Okay. Without giving input, how it is producing a continuous oscillation means because of the thermal noise present in the circuit, that helps to provide a little bit voltage fluctuation. Okay, that is produced using this tank circuit. That voltage is, the part of this voltage is fed back to the voltage amplifier circuit. Okay, whatever the losses happens in the tank circuit, that will be compensated using this amplifier circuit. Okay, this is the design of that one. Now first we'll see how to rig up this circuit, then we'll see the output and all. In order to rig up the circuit, as I already explained half of the portion how to rig up the circuit, I maintained that circuit as it is. Okay, till this capacitor, I have maintained the circuit as it is from the experiment 1. Okay, in addition to this circuit, I just had the capacitor and the inductor. Okay, now let's see. If you compare the experiment 1 with the experiment 2, the only changes you observe in experiment 1 and experiment 2 is, in experiment 2, we are not giving the input voltage which we were earlierly giving in experiment 1. As I told earlier, the oscillator is a self-driven circuit. It has to generate the output signal without the input voltage. So that's why we have removed this input voltage, and also in addition to this entire circuit, we are given a tank circuit. Now I'll connect the tank circuit and also the feedback from the tank circuit to this capacitor. In order to connect the tank circuit, we need two capacitor. We have designed the values of capacitor and inductor. I need 1 nanofarad capacitor and also 2 nanofarad capacitor, which is connected in series, and also 3 millihenry inductor. Okay, this is a inductor box. That means we call it as decade inductance box. This is a variable inductance box, and these are the capacitors which we are using for our experiments. Okay, now I'll connect this one. You see the circuit diagram. From one end of the 0.47 microfarad capacitor, this is the 0.47 microfarad capacitor. From the other end of this 0.47 microfarad, we need to connect it to one end of the inductor and also one end of the 1 nanofarad capacitor. This is 1 nanofarad capacitor. All three are 1 nanofarad only. Okay, I'll take one of the capacitors and I'll connect that to the other end of the capacitor. Okay, this is this connection, 1 nanofarad capacitor connection. Now to this point, I also need to connect the positive of the inductor. So this is the inductor box. I'll take positive of the inductor box and I'll connect here. Fine. Similarly, I need to use the 2 nanofarad capacitor. Okay, because we don't have 2 nanofarad capacitor, we are using 1 nanofarad capacitor and we connect that in parallel. So where I need to connect this 2 nanofarad to one end of the 1 nanofarad capacitor. This is the other end of the 1 nanofarad capacitor. I'll connect here at some point. Since I want 2 nanofarad, I don't have 2 nanofarad. So I'll use 2 1 nanofarads and I'll connect in parallel. That will give you 2 nanofarad value. Okay, I've connected this. Fine. Now, if you look at the circuit, between 1 nanofarad and 2 nanofarad, we have connected to ground. So, I need to connect that to ground. This is the in-between values that I need to connect to ground. I am giving it to ground. Okay. And also, the other end of the capacitor and the other end of the inductor has to be given back to the transistor. Okay, that is the other end of the capacitor of the transistor design. So this is the other end of the inductor box, and this is the other end of the capacitor, that is 2 nanofarad capacitor. I'll connect this here. Then from this point, this is the point, from this point I need to go back to 0.47 microfarad. This is the point. From here I need to go back to 0.47 microfarad. This is my 0.47 microfarad. I'll connect to that point. That capacitor is connected to base of the transistor. Okay, that is the circuit rig up. Now I want to see the output. If you want to see the output, definitely we don't have an input channel for this one. So as I told earlier, since it is a self-driven circuit, only we can see the output. In order to see the output, I have used one channel of CRO. Okay, so from the positive of that, I need to connect to this point. That means this is that point is 0.47 microfarad. Okay, I am giving there the positive of the CRO, and negative of the CRO, as you can see, you can give it to ground. I have given it to ground. Okay, and in the inductor box, as I told earlier, we have designed it to either you can give 3 millihenry or 4 millihenry. You can see the variations of the inductance box. I want 3 millihenry. So what I do is, now this is pointing in, you need to see the unit. It is showing 1 millihenry. Right now this notch is pointed to 0. I want 3, so I rotate it to 3. Now you can see it is 3 into 1 millihenry. That shows it is 3 millihenry. Okay, this is how you need to rig up the circuit. Now we'll see what is the output and what we're going to measure in that one. Okay, since we are done with the circuit rig up, now we'll see what is the output. In order, the only supply we are giving is DC supply. So I'll switch it on the DC supply, and we need to set it to 12 volts. It is already in 12 volts. Now we need to see the output in the CRO. The output is coming. You are getting a waveform. Here what you need to measure is, you just have to measure the frequency of oscillation, at what frequency the oscillated signal is producing. Okay, in order to measure the frequency, okay, you need to check what is the time taken for one cycle. Time taken for one cycle. If you see this one, this is making one complete cycle. So that means it is covering almost 2 boxes. Okay, 2 boxes into time per division. What is the time per division? You need to check this knob at where it is pointing. This black color is pointing to 5, and what is the unit? It is microsecond. So it is pointing to 5 microsecond, and how many boxes it is covering? It is covering 2 boxes. So that means it is 2 into 5 microsecond. That is the time taken to complete one cycle. But what we need frequency of oscillation. What is the frequency of oscillation? It is the inverse of time. That means F is equal to 1 by T. F is equal to 1 by T is the frequency of oscillation. What is the T we got? We got it is 2 into 5 microsecond. That means it is 10 microsecond. But I want frequency. So what I do, it is 1 divided by 10 microsecond. If I take it to the numerator, it will give approximately 100 kilohertz. The frequency of oscillation is 100 kilohertz. Okay, this is what the experiment is all about. Thank you.